Let's try and solve this equation. 2 raised to the power of x plus x is equal to 5. Now it may seem that this question can be solved using normal algebra, but let's try and isolate and see. What we can do is say 2 raised to the power of x is equal to 5 minus x. At this point, I think it's quite clear that there's going to be a problem. How do we then isolate the x? Using logs is not really going to work. So this is an example of a transcendental equation. And transcendental equations, in this case, is an equation that is mixing an exponential equation, like we see right here, and a linear equation. Now we can't really solve this using algebra, but there are two options that we can use. Option one is trial and error or graphing it. So option one. So I'm going to test different x values and try to get as close as possible to the actual solution. So if I substitute x equals 0, 2 to the power of x will equal 1, and 5 minus x will equal 5. Now if I substitute 1, 2 to the power of x is going to equal 2, and 5 minus x is going to equal 4. The goal here is to have these numbers be equal to one another. Let's try and substitute 2. So 2, I'm going to get 4 here, and I'm going to get 3 here. So there's been a change. So that gives me an indication that my solution lies between 1 and 2. Let's try 1.5. So when x is 1.5, 2 to the power of x is going to equal 2,83, and 5 minus x is going to equal 3,5. So we're getting a bit closer. Let's try 1,6. If I try 1,6, 2 raised to the power of x is going to equal 3,03, and 5 minus x is going to equal 3,4. So we are getting closer. Now let's try 1,7. 1,7 will give me 3,25 and 3,3. So nearly there. Now let's try 1,75. If I substitute 1,75, I'm going to get 3,36 and 3,25. Now again, there's been a switch here. So it means that my solution lies between these two solutions, between those two values. So let's try 1,73. So if I try 1,73, I'm going to get 3,30, and I'm going to get 3,27 here. Now that is pretty close. So we can say that the solution for x is going to be roughly 1,73. But if you want the actual solution, we need to use a different method. Now we can plot these two functions, 2 to the power of x and 5 minus x, and we can get a more accurate answer. We can see that x is actually 1,71562. Now the second way we could solve this is by using something called the Lambert W function, also known as the omega function. Now essentially what it says is the following. If we have an equation that is u multiplied by e to the power of u, and if we wanted to solve for u, we can take the Lambert W function of this, and the output will be u. Now we're going to use that identity to try and solve the equation that we have. So our goal is to write this equation in the form u multiplied by e to the power of u. Now, it's not necessary for us to actually have U. There are Greek letters that are associated with it, but I'm using U just for simplicity. I'm going to rewrite 5 minus x. I'm going to substitute it for something. So I'm going to say let t equal 5 minus x. That means x is going to equal 5 minus t. So I can rearrange or rewrite this equation now as 2 to the power of 5 minus t is equal to t. Now I can break up the left hand side. 2 to the power of 5 is 32 and multiplied by 2 to the power minus t, and that's equal to t. Next, I'm going to take the 2 to the power minus t across, because basically what it is 32 divided by 2 to the power of t, and that's equal to t. So I'm just going to take it across. So I'm going to have 32 is equal to t times 2 to the power of t. Our goal has e in. Now, so what that means is we've got to get rid of this 2 and replace it with e. Now, say we had an equation, and the equation was e to the power of x is equal to 2. If I wanted to solve for x, I can take the natural log of both sides. So ln of e to the power of x is equal to the ln of 2. Now, the natural log, so ln and e are inverse, so they cancel one another. And so we're going to be left with x is equal to ln of 2. So I can rewrite this as e to the power ln of 2 is equal to 2. So I'm going to take this and replace it there. So I'm going to have 32 is equal to t multiplied by e to the power ln of 2 raised to the power of t. Now I can use my exponent rules, and I'll have 32 is equal to t multiplied by e to the power of t times ln of 2. We need to do a u substitution, because remember, my goal is to have u there. Again, it doesn't really matter, it can be anything. I'm just using u because I want to have it in this form. So I'm going to say let u equal t times ln of 2. That means t is equal to u divided by ln of 2. So my equation now is 32 is equal to u divided by ln of 2 multiplied by e to the power of u. So I can take this across. I'm going to have 32 multiplied by ln of 2 is equal to u multiplied by e to the power of u. And that's our goal, that's what we wanted. So at this point, I can take the Lambert function. So I can take the w function of both sides. So w of this is going to equal w of that. And we know the output is going to be u. So that's going to equal u. So w of 32 ln of 2 is equal to, we don't really need this now, this is equal to u. Now we know that u is equal to t ln of 2, and we know that t is equal to 5 minus x. So let's replace this. So it's simply going to be 5 minus x multiplied by ln of 2. And now I want to isolate here so I can solve for x. So we'll divide both sides by ln of 2. So w 32 ln of 2 divided by ln of 2 is equal to 5 minus x. Now do some rearranging. We are going to get that x is going to equal 5 minus w 32 ln of 2 divided by ln of 2. And you need a special calculator to do this. So when you use that, you can use Wolfram Alpha or some other calculator. You get an answer of 1,715,621.